Well, greetings, students. Today we're going to take a look at Chapter 10 from your textbook, which deals with reaction rates and chemical equilibrium. Reaction rates really refers to how fast a reaction proceeds. You can see that a banana ripens relatively quickly in this diagram, whereas, so here's a banana here, the tarnishing of silver takes a period of a little bit longer, months, and aging, which is a kind of a reaction, takes even longer. So the objective here is to determine how reaction, what kind of factors affect reaction rates. Now this diagram illustrates how two molecules, one being nitrogen and one being oxygen, and you may remember they're both diatomic, there's two atoms per molecule, that they can interact by colliding with each other to make two molecules of nitrous oxide and nitric oxide. And in order to do that, the molecules have to hit each other with sufficient energy, okay, and they have to be in the right orientation. And of course, there has to be enough molecules to actually have this reaction occur. So we can see kind of intuitively that in order for something to occur, you have to have the reactants collide. They have to hit each other in the right way, and they have to have sufficient energy for the reaction to proceed. Now you may remember this diagram from earlier on where we were talking about endothermic and exothermic reactions, but for virtually every reaction we have a kind of barrier to the reaction going from reactants to products, and that is known as the activation energy. Okay, and that's the initial energy required to break the bonds between the atoms. And the rate of reaction is determined by measuring the amount of reactant used up and the product formed. Okay, so notice here we have rate of reaction has to do with changes in the concentration of product and reactant over time. So rate of reaction is change. It's a rate, okay? It's something happening per unit of time. And again, the factors that can affect that are temperature. As you can imagine, higher the temperature, the more collisions, the more energetic the collisions, and change in the concentration of the reaction, of the reactants, okay? And then also this idea of a catalyst. As you recall from earlier on, a catalyst reduces that activation energy. So let's look at temperature first. What does temperature do? Well, it makes the individual molecules that are reacting move faster. Okay, they collide more often and with more energy. And this is a good rule of thumb that I think you should know. It's kind of very handy, and that is that for every 10 degrees increase in temperature in centigrade, okay, most reaction rates approximately double. So you could even use that in terms of how fast is food going to degrade in your refrigerator. Every time you store it at 10 degrees centigrade lower than say room temperature, you roughly double the amount of time that the food can be stored. So that's kind of an interesting little factoid to keep in mind. So another factor is the concentration of reactants. Obviously, as you have more reactants, you have a faster conversion of the reactants to products, okay? So if somebody was counting molecules of product made, well, if you're starting out with more molecules of reactant, obviously you're going to get more molecules of reactant made per unit time. And that's what we define as a faster reaction rate. Then the other factor, of course, is catalysis. And we know that what happens with catalysis is that this activation energy is reduced, okay? So this is activation energy without catalyst and with the catalyst. And of course, the other thing to remember about catalysis is that the catalyst is not changed in any way. It's not consumed or added to. Just summarizing here factors that affect reaction rate: increasing temperature, more collisions, faster reaction; increasing reactant concentrations, more collisions, and per unit time, so that's faster reaction rate. Addition of a catalysis lowers the energy of activation, so that also increases reaction rate. So here's a nice little study check. Take a minute to see if you can answer these questions on your own. And you can see that, as you might expect, raising the temperature increases reaction rate. Removing one of the reactants decreases the reaction rate. That is, just to make that clear, so if you had less molecules of oxygen to react with carbon monoxide, at any point in time, you would have fewer carbon dioxide molecules being formed per unit time. Adding a catalyst would increase the reaction rate, and lowering the temperature, well, obviously that's just the opposite of raising the temperature. So here's a little diagram that's kind of interesting that shows you what a catalytic converter does. So a catalytic converter has the word catalyst in it, which means that the catalyst is neither is not used up during the process. And basically, this is generally a microporous platinum, which is in this catalytic converter. And these days, it's interesting that catalytic converters are actually being stolen from cars so that they can be sold for their platinum concentration. But you can see it takes these exhaust gases and processes them. Basically, here's what's going on. You have nitrogen oxide or nitric oxide the oxygen is removed, and leaving you with nitrogen gas and oxygen, which are not harmful to the environment through their catalysis of the reaction that occurs on the surface of the platinum. And conversely, you have carbon monoxide, okay, which is a poison, that the oxygen being added to that. So it's taken away from the nitrogen oxide and added to the carbon monoxide to make carbon dioxide. Again, that reaction occurring on the surface of the platinum, and we're getting carbon dioxide, which is a greenhouse gas, but on the other hand, at least it's not harmful to human beings or to life. So now let's move on to another concept, which is chemical equilibrium. And this is just illustrated by virtue of this reaction, which shows hydrogen and iodine in a gaseous form reacting to form hydrogen iodide gas. Now, here's the thing to keep in mind. This reaction, as in many reactions, can occur in a forward or reverse direction. If we turn this around, we could have had hydrogen iodide as the reactant, forming H2 and I2, hydrogen and iodine, as the product, okay, if we just reverse that reaction. So while the reaction is proceeding forward, okay, in this case, hydrogen and iodine gas making hydrogen iodide molecules are also, at the same time, once they're formed, they're breaking down to hydrogen and iodine. So the reaction, not all reactions are reversible, but some are, and this is an example of one that is. The balance of these two processes is called chemical equilibrium. So just to kind of look at this a little bit more, we have the forward reaction here, the arrow going in from the left to the right. And then we have the reverse with the arrow going from the right to the left, okay? Two rates, one rate forward, one rate going backwards. Again, this slide is just showing you again how you would actually, if you wanted to literally write the reverse reaction in kind of standard way that people understand it, it would be hydrogen iodide going to hydrogen and iodine. So you could actually get the equilibrium to occur by either starting with hydrogen and iodine, or by starting with hydrogen iodide. Okay. So as it mentions here, in the case of the forward reaction, as hydrogen iodide builds up, the rate of the reverse reaction increases while the rate of the forward reaction decreases. So again, because we start with what we call reactants, the rate of the forward reaction as the reactants are being depleted goes down. The rate of the reverse reaction as the reactants are, hydrogen iodide in this case, are being produced, the rate of the reverse reaction, okay, goes up. Now somewhere along the time axis, they balance out each other, okay? The reverse and forward reaction rates are the same, and that's when we get equilibrium. Now, at that point, the concentration of reactants and products is no longer changing. So here's a nice illustration of that concept, okay? So take a minute to try to understand this. It's also one of your homework problems. If we look at concentration reactants, right? And reactants are what's in blue or what's in white, pure blue, pure white, okay? And then the products are the combination of white and blue, okay? So if we look at, let's say, concentration reactants, we have 1, 2, 3, 4, 5, 6, 7, 8 reactants, 4 blue, 4 white. Now as we go forward, we see that the concentration of reactants, okay, either straight blue or straight white, begins to go down. It's 6, now it's 4, now it's 2, oh, now it's still 2, okay? The reactions of forward and backwards are still going on, but there's no net change. Or we could look at the concentration of products and begin with, okay, that's all reactants and no products. But as we move forward, we see that we have more and more product formed. At one point, again, here from 3 to 8 hours, there's no net change. So we're at equilibrium. So one could say, looking at this time frame, that once we're at 3 hours, we are at equilibrium. The rate of the forward reaction, the rate of the reverse reaction are the same. And I think this is a nice slide just to show you that you really need to keep in mind that it's somewhat arbitrary to say, reactants and products here when you have a reversible reaction, because regardless of what, here's a reaction where SO2 and O2 are going to SO3. Sulfur dioxide and oxygen are making sulfur trioxide. So we could say that the reaction, if we start with sulfur dioxide and oxygen, we're making sulfur trioxide, right? Here's sulfur trioxide. That's the forward reaction because we are starting with these two reactants. Or we could say, well, let's say we started with SO3, sulfur trioxide. If that was our reactant, then the products would be SO2 and O2. All right. So either way, we could, when we're talking about reactions in equilibrium, the bottom line is, regardless of what we're calling reactants and products, we end up with the same equilibrium of the two at the end of the day. So here's a nice study check to kind of wrap this up. Reactants, yeah, so take a few minutes to look this over and see if you can answer it. And let's go ahead and go through this. Now, reactants form products in the forward reaction, and that's really just a consequence of the way chemical reactions are defined. We call what's on the left the reactants, we call what's on the right the products, and that is defined as a forward reaction. Okay? At equilibrium, the reactant concentrations does not change, and the product concentrations do not change. Okay? So there's a balance between the reactants and products that does not change. The individual molecules, by the way, I know this is confusing, but the individual molecules may reform, but the net effect that there's no change. Okay? Products form reactants in the reverse reaction. Okay, so that's just, again, the way we define things. Well, if we're looking at moving from what we see on the right side of a chemical equation to the left, we're talking about going from products to reactants. That's, by definition, the reverse reaction. Okay, I think that kind of wraps it up. I hope you understood the material. I think the book does a nice job of explaining this if you were unable to follow some of what I was saying. I know I went through it quickly, but you can always listen to it again, and you'll understand things much better when you do the assigned problems. God bless.